it. Alright, string theory. String theory is a theory of a universe that tries to unify general relativity with quantum mechanical effects. These two theories of the universe that are both right on their own scales, but they don't seem to agree. They imply contradictory things. So it's still a work in progress, and there's a lot of workarounds and like stuff. It's like completing a puzzle, but you like keep changing things, and you have to like make all these ideas that sound ridiculous. Anyways, so string theory to work, it requires 10 dimensions of space, and a way to imagine this is that these 10 dimensions of space are in our world, and M theory is similar to string theory, which suggests there are 24 or 25 or something like that. But how would a three-dimensional universe like ours, where it cannot have a fourth axis, how could we be living in 10 dimensions? Well, imagine a telephone wire and an elephant, and be looking at the telephone wire, it would look completely one-dimensional. But the elephant, the telephone wire is one-dimensional, see? So from the elephant's point of view, it would be. But if you look really close, you zoom in on it, in on it far enough, you can see that it's actually a three-dimensional structure that's really long in one dimension, but has these two tiny curled up dimensions. You can see the little cords going around like this. There might be like a beetle on the telephone wire. And it actually is a three-dimensional structure, but one of the dimensions is so huge, and the other two are tiny, they're compressed, they're curled up. And the idea of string theory is that there could be 7 more tiny curled up dimensions. If you go really far down, like past the scale of the elementary particles, like 2 times further than you have to go from a meter to the whatever quark is the smallest. And you can get to these tiny distances where you could actually draw 10 axes perpendicular to each other in our space. And there'd be like fluctuations going on all the time. It'd be really crazy, but it's the theory that our universe has that many dimensions. Again, the analogy of the curled up dimensions, kind of like the telephone wire. The elephant would only see 1 dimension, but an ant or a beetle on the wire would see 3. And maybe if you could have something small enough, it would be able to see 10. And, alright, so this is where it gets really interesting. So this is the... Now I'm going to get into the section where we don't really know much about these things. I'm going to talk about next. Like, with 4 dimensions and 5 dimensions and, like, these conditional properties, all the stuff I've been telling you, like, we can run computer simulations on that. We have analogies. We have, like, our flatland analogy. Those can help us out so much with understanding and everything, but these things are going to be even more crazy. But since you understand 4D, it's probably going to be a bit easier, but trying to understand what the implications of these other things I'll tell you about are, it's going to be really hard to do. So negative spatial dimensions. What do I mean? Well, if you can have 1, 2, 3, 4, 5, 6, 7, 8, and 0, at least that's the point, why can't there be a negative spatial dimensions? Why can't you have negative 1? That doesn't really make sense, because you'd have to have negative 1 perpendicular axes, negative 2 perpendicular axes. What does that mean? That doesn't really make sense. A process you can imagine getting to that would be taking a sphere, taking out the point from the top, and like kind of flattening it out, kind of like taking an inflatable ball and puncturing it and flattening it out into a circle. Take out, now it's 2-dimensional. Take out the inside, poke a hole, like slice it. You can have a 1-dimensional line. You can repeat this process, and after the line, you hollow that out, you cut out one of the points. Like, there isn't really anything more to do, but what if there was a way to get to negative spatial dimensions? Like, it might be impossible, it might not be a real thing, or it might require a different mathematics than we have, different geometries, which, as crazy as it sounds, there were these people a long time ago who figured out that you could have a geometry system in which like, things like, you could have, like, I don't know, but there were these, like, contradictory things that don't make sense in geometry. You could, like, imagine these ridiculous things, and you could base a whole geometry off of them, and they would actually make sense. So, trying to remember what it was. So, alright, so if you have a line, this geometry theorem states, and you have a point, there can only be one parallel line that runs through the point that is parallel to the first line. But there was a theory of geometry invented that says there could be 2 parallel lines that are attached to the point that could pivot around it, to that first line. but that doesn't make sense. That's not possible if we look in our geometry. But they made a whole theory out of it, and there weren't any paradoxes. It didn't make sense, really, but it didn't imply any contradictions. So that geometry is just as right as ours, but it would probably take a different universe to have that geometry, and that's really interesting to think about. Alright, so that's the negative spatial dimensions, and yeah, let's just don't think about that too much. It might be tricky. Like, it's probably not worth thinking about too much, but who knows, there might be such thing. Alright, so remember when I told you earlier that I wasn't talking about time when I was talking about the fourth dimension? Now I'm going to talk about time. Time as dimensions. Time is one-dimensional as we know it. There is the past, there's the future, and we can draw a timeline, put all our events on it. Any point in time can be described as a number, one number. Now, of course, we have the year, we have the month, the day, and the hour. But those are all conveniences to make it easier. But there actually is the Unix time system that timestamps are given to. The computers use this time system, 32-bit integers, starting from the first second of 1970. And each second has its own number. And we have enough of these to last until 2036 or 2038, and then we're going to run out of those numbers, so we're going to have to go to a 64-bit system or something. But anyways, that system uses each second as one individual number. Because time is not like an array, it's just like one line. You can plot it out. It's one dimension of time. Now, you can't travel through it however you like, but you can see that it's one-dimensional structure. So you wouldn't call our universe four-dimensional. That would be misleading. You could say four total dimensions, but if you say four-dimensional, that sounds like you're saying it's four-dimensional spatially. And if you say one-dimensional, that sounds like it's one-dimensional spatially. So to do this, we usually say n plus t dimensions. So if we say our universe is 3 plus 1 dimensional, that means it's 3 spatial dimensions plus 1 temporal dimension. And so the Flatlander's universe would be 2 plus 1, 2 spatial plus 1 temporal. Again, saying we live in 40 would be confusing. 40 universe would be 4 plus 1. So, and a picture is zero dimensions of time because it is not changing, so it doesn't have a timeline. Instead, it just has a time point, right? It is a snapshot. So a picture, like a hologram that was still, for example, would be 3 plus 0 dimensions. So we can have 0 dimensions of time, that's a still image, or 1 dimension of time, where things are changing. But why does 1 have to be the limit? Well, that doesn't make sense, does it? Well, once I was on this walk and I was thinking about Lineland. I was thinking, what if they wanted to learn about extra spatial dimensions like we do, like I've been talking about? The problem is that they do not have any flatland they can compare it to. Like, we have flatland, we can think of that. In Flatlanders, they could use the analogy of a Lineland, a one-dimensional universe. But Linelanders, imagine a one-dimensional universe, completely one-dimensional. Everything on it was one-dimensional, so it would be a 1 plus 1 dimensional universe, probably. They would not be able to imagine 2 or 3 dimensions. They would not be able to have a lower dimension to draw on. They could imagine a point, a zero-dimensional universe, but that doesn't really do us much more than we can imagine further than imagining a photograph and a moving video. Like, it's hard to imagine what comes after that. So a zero-dimensional, it's not really much of a... You can't really use it as a launch pad as much. So these one-dimensional critters, they'd be stuck in their one dimension, and they would go on, and they would never question why the number of dimensions was 1. In fact, they probably wouldn't have a concept for dimensions because there would be one dimension of space and one of time. There would be no sense of perpendicularity. You could not have a perpendicularity to this space. So they'd be stuck like that. They'd be stuck in one dimension. They wouldn't even be able to think of more. And I thought, what if our universe is like that? What if our universe is like that where we have one thing, one dimension of something, and we can't have more? And we can't think of a lower analogy that's still a counting number that we can get up from. And I was like, oh, time is one-dimensional. But would it make sense if you could have a timeline, like events this way, and would it make sense if you could have angles of time, like perpendicular, like a time map, like you could have a map? It would have to flow. It wouldn't be like this. It would be really, really weird. And we just can't really imagine how it would be, but it must be possible. The thought is that we just can't imagine what two-dimensional time would look like, just as one-dimensional Linelanders would not be able to imagine two-dimensional space. If we tried to explain it to them, it wouldn't make sense to them. The whole idea of slope doesn't make sense. Rise over run, rise and run, how are those different? Perpendicularity, they don't understand that. The only way would be to show them, but if you can't do that, it's almost impossible to tell them. They would not be able to understand the concept of 2 or 3 or 4 dimensional space. even though we can understand higher dimensional space, they would not be able to be, because they wouldn't have anything to draw off of, any sort of launching pad for that. Similarly, we don't have anything much useful to compare for higher dimensional time, so we're stuck in one-dimensional time, and that's all we know of. And so we're like always pretty ignorant about 2 or 3 dimensional time, even though that could work, but it wouldn't make sense.